Hello, you beautiful people. In the last video, I showed you how to get the reactor sizing for the recycle flow reactor, and today I want to show you the application and how you can use the formula in the rate conversion diagram. Okay, the formula from the last video was this, and now let's have a look how this should work. Okay, here we have our residence time is the inlet concentration, so we don't have the inlet concentration in here, but it doesn't matter. And the first thing we want to have a look at is the integral here. Okay, we want to have, as in the other cases, we want to have a outlet conversion of 80%. So this is the dotted line here. And I said, okay, let's have a look at a recycle reactor with a recycle ratio of 3. Then we can easily calculate the inlet conversion. So this is R over R plus 1, so 3 over 4 times our 80%. This means 60%. Okay, this is our second case. And now we have to evaluate our integral from xa equal to 0.8 to xa 0.8, so 0.6 to 0.8, 1 over r dxr. Okay, so this means we just go here and we have to solve the integral. Okay, so we need something like this area here, and so for me it's easier to have the area as a what is it, not a square, as a rectangle. So maybe this would be something like this. So what you have to do is you just have to make sure that the areas here, they should be the same size. So we have this small rectangle here. Hopefully this is almost the same size as this one. So and if you do this, then you have your rectangle. This should be something like this. Okay, so with this we have this part of the expression here, but we have to multiply it by r plus 1. So r plus 1 is 4. So here in this case this is 4. So we need 4 times this area. And if you have a look here, okay, so this is the difference here is 0.2. If you multiply this by 4, then you will find out, okay, it's the total length from the beginning till the end. So if you want to know how big should be your recycle flow reactor, then you just have to multiply your area by 4, by r plus 1, and then you know, okay, let's say blue. So this area here, this is your residence time over your initial concentration. Okay, then let's have a look how we can calculate it. If you look here, I can stay with blue. Tau over CA0, or tau the same as CRE 0 times 4 times this area. And if you want to evaluate it, so this is, you have here a difference in your conversion of 0.2. This is without units, and then you have to multiply it with 1 over r, and here the mean value should be something like 110, and then your units are minute, cubic meter over kilomoles. Okay, and your Ca0, this was 1 kilomole per cubic meters we always had in the example. Okay, this means 1 times 4 is 4. 4 times 0.2 is 0.8, and times 110, so you should end up with 88 minutes as a residence time, and this is your volume over your initial volume flow. So I think after all this mathematics that we did and this not so nice equation here, if you look at it in the diagram, I think it's rather easy to use. Just for a little practice, we want to repeat it with a recycle ratio of R is equal to 1. So if the half of your reactor outlet is recycled and the other half is leaving the reactor. Okay, then you end up with the inlet conversion of 0.4. Same procedure, so your normal area would be this. Then you have to somehow estimate what is your mean conversion. So the blue area and the orange area should be the same. I would say maybe this is a value of 90 minutes cubic meters over kilomole. And then you have to take into account that you have to correct it. So this is 2. So here you just have to double your rectangle, and this means, okay, now your total area, or your total residence time divided by the concentration should be this rectangle. So here this should be residence time over Ca0. Okay, if we now want to go for this, Ca0 times R plus 1 times your concentration difference 0.4 times this 90 minutes cubic meters per kilomole. So this again was 1. I skipped the units. This is 2. Then you have 0.8 times 90. So now you should have a residence time of 72 minutes. And again, this is your reactor volume divided by the initial volume flow. Okay, so here you have the 2. Okay, so you can see if we would go here for for a recycle ratio of 1, then it would be rather easy. Then you would just have the area below the curve and you would have an even lower residence time. Always for the case of the isothermal conditions. Okay, so let's summarize for the recycle reactor. For the recycle reactor, we found this new equation, and I think this equation can be used quite easily for the diagram that I just showed you. So the inverse of your reaction rate on the y-axis, the conversion on the x-axis, and then you can very easily use this expression here. Other options would be, of course, you can solve integrals. So you tried this in the worksheet number 4. So looking it up in table of integrals, or you can solve it numerically. Or you can, of course, this is always possible, you can use the Euler scheme and you can simulate your reactor, and this can be done, for example, with MATLAB or Excel or whatever you like. So, and for further practice, I will make up a new worksheet 5 for you where you can practice a little bit about the recycle reactor. Okay, thanks for watching and have a good day.